Okay, phase portrait for the potential V of x equal to x cube by 3 plus ax square by 2. Okay, that's the potential energy curve, potential energy versus x that's given. So this, since we have already discussed in some detail, we'll just quickly go through this. You can do this by yourself, the rest of it. Okay, the first point is to plot, the first thing to do is to plot V of x versus x. For that, the first thing is that we find the zeros of the potential energy. We see that the potential energy becomes 0 at x equal to 0 and x equal to minus 3a by 2. So we already get some idea. We note that at x equal to 0 and let's say at some minus 3a by 2, it is 0. Okay. The next point is to find the extremum points. All right. You take dv by dx equal to 0, which says that x square plus ax is equal to 0. Is that correct? Yes. All right. Now you solve for this. X into x plus a is equal to 0, or x equal to 0 and x equal to minus a. So there are 2 points where it's 0. It's at x equal to 0 and, sorry, it's 2 points where it's an extremum at x equal to 0 and let's say x equal to minus a. All right. So what do we have? Let me just repeat it here. We know that it's 0 here and we know that it's 0 at minus 3a by 2. We will for extremum point, all right. Minus a, it's an extremum. For 0 also it's an extremum. Now we need to see what kind of extremum these are, right. So we take the second derivative, right. You take the second derivative, it's 2x plus a, and you check at this extremum point. The one extremum point was x equal to 0, right. So you take 2x plus a at x equal to 0. You see that it's positive, so it's a minimum. Right. So we see that this is a minimum. This point is a minimum. There's a minimum here. All right. And similarly, you see that at x equal to minus a, which is another extremum point, all right, which I have marked here, it's a maximum. Right. It's a maximum. At x equal to minus a, this is a maximum. All right. So we know that we have got a maximum here. Okay. Now what we do is, let's just check here what's our V of x cube by 3 plus ax square by 2. It's x cube by 3 plus ax square by 2. Right. Now let's find the value of this potential energy at x equal to 0 at the minimum point. All right. Let's find the value of the potential energy at x equal to 0. We see that it's equal to 0. So V of x is 0 at this point. We have got one more information. We already saw that this is equal to 0. But let's find V of minus a because it's a maximum. Right. V of x, V of minus a is, you see that we saw that it's a maximum. So you put minus a cube by 3 plus a into a square, right? Yeah, a square by 2. So that's minus a cube by 3 plus a cube by 2. Is that correct? So what's that value? It's 6 and minus 2a cube plus 3a cube. So it's around a cube by 6. Am I right? Yeah, it's a cube by 6. So value of the potential energy is positive. It's a cube by 6 and we know that it's the maximum. So the maximum height is somewhere about a cube divided by 6. So if let's say a is 1 for example, then a cube by 6 is around 1 by 6. So that's not nice. So let's take a equal to, we just need to get the qualitative behavior, all right. If you take a equal to 3 or something, it becomes, or a equal to 2, it becomes 8 by 6. That's just about above 1. Okay. So we see, now we have got the details. We know that this is a minimum, so it has to increase on both directions from here. Okay. This is a minimum, we said, so it has to increase in both directions, all right. And it reaches this point and then here it hits a maximum. It hits a maximum. Did I write wrongly? This is a maximum, right? Yeah, this is a maximum, right? And then if it's a maximum, it has to decrease on both directions. It's decreasing here, fine, it has to decrease along here also. So this is our potential energy curve. This is our potential energy curve. Okay, I hope this is clear. So these details are sufficient to fix the potential energy curve, right? So I'll just go through the steps again. The first thing is that we found the points where the potential energy is 0. Okay, then we found the extremum points, and the next thing we did is that we found whether the extremum points are a maximum or minimum, and we saw that this is a minimum and this is a maximum. If this is a minimum, it means that it has to increase in both directions. If this is a maximum, it means that it has to decrease in both directions. And we also had an estimate of the value of the height of the potential energy at this point. at this maximum. At the maximum, what's the value of this height of the potential energy, by just substituting that minus a inside the potential. So what's the value of the potential energy at x equal to minus a, right? That's what we found, right? So we got the qualitative behavior of the potential energy curve. Okay, let's see. That's it. We have got the potential energy curve like that. Okay, that's exactly what we got here, right? Now we have to draw energy lines. Let's draw energy lines like this. We can have E, okay, let's say this is E1, right? This is below this. We can have E2. We can also think of particles, okay, I think with energy, let's say E less than 0. Let's imagine we can have particles with E less than 0 also. So that's possible because the potential energy is negative. Okay. All right. So that's how we have it here. So we see that if it's within this, right, within this E1 is greater than V along all these points. So this is actually allowed region. This region is actually allowed. All right. So this region is actually allowed, and it will be bound states because you'll see that there will be ellipses in here. Right. So you see that's exactly what we have here for E2. This is the energy line corresponding to E2. Okay. So the particle, this is an allowed region because E is greater than V. So it is just periodic motion. Right. It's just periodic motion. So it's just like the part of that harmonic oscillator potential that we talked about. This kind of a bound state. It's periodic motion. So it's going like that. That's fine. Now this is different. Okay, so we see that it's not exactly bound here, right? It's not. Let's talk about this first. Let's talk about this one first. Okay, so we drop a point here. We know that the momentum will become 0 at this point. And we see that, let's imagine a particle coming from minus infinity. Its momentum will increase. It will never become 0, all right? It will become a minimum here. It's supposed to be a minimum here. It will become a minimum at this point, right? This is the point where the momentum is minimum, all right? And then again it increases, and then it encounters this point. The momentum again decreases, all right? Because the potential energy first decreases and then increases. So the momentum becomes 0 at this point and then turns back, and we have got these trajectories. Okay. Now we can think of particles with energy E2 again. We can think of particles with energy E2 which are outside, all right, coming from minus infinity, and you will see that it comes from plus infinity, and you see that it has a classically forbidden region and it goes back, right? Because at this point the particle coming from minus infinity, it will come, the momentum will decrease, and then it will go back, all right? Because you see that if energy is E2, inside this, right, for example, the height of the potential energy, okay, this is the height of the potential energy, this is the height of the energy, you see that V is greater than E or E is less than. So this is classically forbidden. This region is classically forbidden, all right? Similarly, for particles of slightly greater energy, we have got hyperbola here. So we have got all sorts of things here. Now what about particles with exactly energy E, this energy E? What about these particles, all right? These particles, we see that all right, they will come from infinity. Yes, it reaches here, and then, okay, there are trajectories like that. These are separatrices in this case, right? Because it actually separates two kinds of motion. We have got a bound state, a periodic motion here, and a particle coming from minus infinity and going to plus infinity. Right? So these are separatrices. Okay? Now just by drawing the potential energy curve and drawing the energy lines, it's easy to plot these things. So we see that particle coming from plus infinity also is possible, but you see that all the regions are classically forbidden. All right, there can be particles coming from plus infinity, but all these regions are classically forbidden because this energy is less than the potential energy. Okay, E is less than V. So this region is classically forbidden. So we don't have any hyperbola here. Okay, I hope this is clear. The next problem is the phase portrait for a simple pendulum. Right, it's a very familiar system. Let's look at how the phase portrait are. All right, so the potential energy curve is like this. The potential energy as a function of x is given by this thing. All right, it's 1 minus cos x, so you can write a sine square x by 2, which means that it's positive everywhere because it's sine square. All right, now we plot, first thing is to plot v of x as a function of x. All right, you know the plot for sine. Okay, we don't have to really do the plotting thing. Right, the phase trajectories are then sketched for energies E1, E2 and E3. That's what we do. Okay, we have got different energies E1, E2 and E3. Okay? And this is the sine square x curve. All right, that's not particularly complicated. We all know how to plot a sine square curve. All right. So we see that this is the potential energy curve. Right? Let's see how the diagram looks. Right? First, let's look at energy E1. Let's look at energy E1. All right? Immediately we see that there are regions which are classically forbidden. For example, this region here, E is less than V. So this region is classically forbidden for E1. Similarly, this region is also classically forbidden for E1. Right? But if it is between these 2 points, what happens is that it has a periodic motion because it just looks like the harmonic oscillator potential in this point. Okay, so we've got this periodic motion. It just looks like the simple harmonic oscillator potential. Of course, it's also a simple harmonic oscillator for small oscillations. All right, so that's what we have got here. Okay? All right, now what happens for this is the case E1, E2. Let's leave E2 for a moment. Let's look at E3. Okay, so here E3 we see that everywhere along the x-axis E is greater than V, right? All along the x-axis, the energy is, total energy is greater than the potential energy. So the momentum never becomes 0. It's square root of 2me minus V. Okay, so the momentum never becomes equal to 0, right? It decreases, of course. So it comes from here, for example, if it's coming from minus infinity, you see that here we are talking about this angles, all right? So this we see that the potential energy decreases. The momentum decreases as as it sees more and more of the potential energy. It decreases, but it never reaches a 0. Right? It goes like that, all right? Now this trajectory corresponds to the case of rotation, all right? If you give it enough energy, if you give the simple pendulum enough energy, it just starts rotating, all right? Now this curve corresponds to a rotating simple pendulum, If it has enough energy, it just starts rotating. Okay, that's what happens, all right? What we have here in between is the separatrix, right? This is the case where the momentum becomes 0 at one point. This is the case where the momentum becomes 0 at one point. All right, so you see that the momentum becomes 0 as you increase x. All right, if in this case x stands for theta. So if you increase theta at one point, if it has just enough energy, at one point the momentum becomes equal to 0. If it has just the correct energy, the momentum becomes equal to 0. All right. Now this is a point of unstable equilibrium. Right? Now these trajectories don't really intersect, but this itself is a point of unstable equilibrium. It remains, if it is there, it remains there forever. Okay, that's what happens. But now if there is a small perturbation, it could either go towards positive x direction or towards minus x direction. So if a pendulum is standing like that, okay, that corresponds to this point. Okay, so if you give just enough energy, it can come and stand here like that. Right, if you give exactly the correct energy, so it reaches a point of unstable equilibrium, but it could either fall towards minus x or towards plus x. All right, this is falling towards minus x, and this is falling towards this is falling towards minus x, and this is falling towards plus x. All right, and this is separatrix. Right? Because the separatrix actually separates between two kinds of trajectories. One corresponding to periodic motion and the other one corresponding to unbound or rotation in real space. All right, so we see that rotation in real space corresponds to an open curve, whereas a periodic motion in real space corresponds to a closed curve here. Right, so in real space it just is the opposite. All right, in this case, in the real space, periodic motion in the real space, periodic motion just goes like this, but the rotation gives you a closed curve. Okay, rotation gives you a closed curve. All right, in this case it's just the opposite. The rotation of the simple pendulum gives you this open curve in phase space. All right, so this is not very difficult. We just plotted the potential energy, we plotted the different energies, we drew different lines corresponding to the different values of energy, and we saw the different cases.